Welcome to this video where we're going to consider how once we have our raw data, we can wrangle it into a form that is useful for analysis. Okay, so let's suppose we've got some data. That's a really great start. You might have had it handed to you by a collaborator, you might have requested it via an API or scraped the raw data from the HTML of a web page yourself. In the worst case scenario, you've been an actual scientist, not just a data one, and you spent the last several months of your life painstakingly measuring flower petals or car parts, and now you really want to do something useful with your data. We've seen already how you can load your data into R and pivot between wider formats and longer formats. But that probably isn't going to be enough to satisfy your curiosity and the needs of your particular data science use case. You'll probably want to be able to view your data, to manipulate and subset it, to create new variables from existing ones, and to cross-reference your dataset with others. All these things are possible in R, and are known under various collective names, including data manipulation, data munging, and data wrangling. I've decided to use the term data wrangling here, and that's because data manipulation sounds boring as heck, to be honest, and data munging is both unpleasant to say, and it kind of makes me imagine that we're squelching through some sort of information swamp. So in what follows in the rest of this video, I'll give a flyby tour of some of the tools for data wrangling in R, showing some examples along the way. I'll focus on some of the most common and useful operations here, and link out to more extensive guides for wrangling your data in R, so you can refer back to those as and when you need them. When I'm demonstrating these wrangling skills, I'm going to use some example datasets. These are the Penguins dataset from the Palmer Penguins package, and the MT Cars dataset, which comes as part of any R installation. So the first thing that you might want to do with your data is have a look at it. There's several tools to do that, and each of these is going to have a slightly different use case. First up is the view function, and this can be used to create a spreadsheet-like view of your data. In RStudio, this will open your data as a new tab, and if you're running R at the command line, it'll open it as a new window. This view function will work for any matrix-like R object. This includes things like tibbles, data frames, vectors, and matrices. One thing to note here, and a common gotcha, is that there's a capital letter on view. So it's capital V on view, not lowercase v. When you're using this view function, it should only be used interactively, and it'll cause problems if you include this in a script that you're running automatically. For larger datasets, you might not want or even be able to view it all at once. In that case, you can use the head function that we've met before to view the first few rows, and remember that we've got an integer argument n that specifies the number of rows that you'd like to return. An alternative way to view a large dataset, or one with a particularly complicated format, is to examine the structure of that object using the str function. This is a really useful way to inspect the structure of list-like objects, particularly when they've got a nested structure to them. So think of things like JSON files that you've read in, or model objects here. Finally, if you just want to access the names of an object, you can do this with the names function. And this will work for a whole range of different types of object. If you're working with a tibble or a data frame, you can more explicitly access the row and column names using the col names and row names functions. In the cars data here, we can see that the car model is stored as the row names. This doesn't really jive with our whole idea of tidy data. We've got information that isn't stored within cells, and we'll see how to fix this shortly. So after having looked at your raw data, you might have to deal with some variable names that are in an uninformative format, or that contain characters that don't play nicely with computation. So things like spaces, for example. This is why being able to rename variables is going to come in. The function that we just met, called col names, can be used to set as well as to retrieve those column names. Here we're renaming the first column of the cars dataset from MPG to the more informative miles per gallon. I'd like to use the original cars data frame again later in this video, so I'm making these modifications to a copy of that data frame that I'm calling cars renamed. Another option is to use functions from the dplyr package to rename your columns. So here, let's have a look at altering the second column name. If we're making alterations to lots of column names, then these can be strung together using pipe operators without having to save any intermediate objects along the way. When using the dplyr function here, you have to remember that the format that we're using is new name equals old name. This matches the format that you use when you're creating a data frame or tibble in the first place, so it should be reasonably easy to remember. But it's the opposite order to the Python function that has the same name, and that catches a lot of people out. In the section coming up on creating new variables, we'll see an alternative way of doing this by copying the column and then deleting the original. So, of course, you won't always be interested in all of your data. Sometimes you're going to need to access only certain rows, certain columns, or combinations of those, and that's where subsetting comes in. I'll start off with a brief recap of how you can do this in base R, where you can extract rows, columns, and combinations thereof using index notation. You specify the rows and the columns that you want to retain from the data frame. Conversely, you can use negative integers to specify the columns or rows that you want to drop from that data frame. In base R, you can also subset using a logical vector. So here we see an example of keeping only the penguins with bills that are more than 70 millimeters long. And finally, you can subset using row or column names themselves. When using column names, these may be specified using either the bracket or the dollar notation. One thing to be aware of here is that these two methods will return different types of object. Since penguins is a tibble, the bracketed example will return another tibble. Subsetting a tibble just gives you another tibble. On the other hand, if you use the dollar notation, this will extract the species column and return it as a vector. As well as base R functions, there are dplyr options for subsetting, and there are two main functions you're going to want to use here. Filter will subset by rows, and select will subset by column. In both functions, you list what it is that you would like to retain. These filter and select function calls can be piped together to make complicated subsets. Again, we can invert the selection that we're doing and do an inverted subset by negating the filter statement. And we can drop columns by selecting all columns except the ones that you want to drop. If we want to invert the subset of rows that we're keeping, we can do this by negating the filter statement. Similarly, we can drop columns by selecting all columns except the ones that we want to drop. The data that you're provided with originally aren't always going to be sufficient. You'll often need to transform or combine them in some way. Again, there are different approaches you can take to creating new variables, depending on whether you use base R or dplyr functions. We can create new variables in base R by assigning a vector of the correct length to a new column name. If we then drop the original column name from the data frame, this gives us that alternative way of renaming columns. One thing to be aware of here is that this operation doesn't preserve column ordering. Generally speaking, code that relies on columns being in a specific order is going to be fragile. It'll break easily. If possible, you should try and write your code in another way that's robust to column ordering. I've done this here when removing the WT column by looking up the column index as part of my code, rather than assuming that it'd always be in the fourth column position. The analogous function from dplyr to create new columns is called mutate. Here we're creating another column that has the car's weight in kilograms rather than in tons. And to keep this easy to look at, I've then selected just those two columns, the original weight and the weight in kilograms. You can also create new columns that combine or are functions of multiple other columns. One useful example of adding an additional row to a data frame is to convert its row names to a column of that data frame. You could do this just as we did before, by first using mutate to add a new column of row names, and then setting the original row names to be null. However, there's a neat function from the Tibble package called row names to column, which will add these in as the first column and remove all of the row names, all done in one step. There's a similar function from Tibble that adds the row ID of each observation as a new column, and that can be particularly useful when you're trying to order or combine tables. Moving on to summaries then. The summarize function allows you to collapse a data frame into a single row using a summary statistic of your choosing. We can calculate the average bill length of all penguins in a single summarize function call. Since we have missing values, we're going to calculate the mean of all recorded values here. But this is something that you should consider carefully in any real data analysis. How do you want to handle those missing values? We can also use summarize to gather multiple summaries into a single data frame. In all, this isn't particularly exciting by itself. You might rightly wonder why you'd want to use these summarize calls when you could just use the simpler base R calls directly. The first benefit is that these summarize calls ensure that you'll always get a consistent output every time you're going to get a Tibble out of this. However, the second and main advantage comes when you want to apply these sorts of summaries to distinct subgroups within the data. So let's have a look then at grouped operations. These allow you to calculate the same summary statistics for each level of a factor with only one additional line of code. So in this example here, we're recalculating the same set of summary stats that we just found for all of the penguins, but then calculating those for each individual species. The only change we've had to make here is add in one group by line to convert the original penguin's Tibble into a grouped data frame. You can also group by multiple factors to calculate summaries for each distinct combination of levels within your dataset. Here we've grouped the penguins by combination of species and the island to which they belong. By default, each call to summarize will then undo one level of this grouping that you've applied. This means that in our previous result, our resulting object was still grouped by species. We can see this by examining the structure of the returned data frame. The first line here tells us that this is an S3 object that we've met briefly before, and the class of that object is a grouped data frame. This in turn inherits its properties from a Tibble data frame, whose properties then come from a Tibble, and finally the base object type of a data frame. Since we've grouped by two variables here, R expects us to use two summaries before returning a data frame or Tibble to us that isn't grouped. One way to satisfy this is to apply a second summary at the species level of grouping, but we won't always want to do that. We won't always want to apply another summary. In that case, we can undo the grouping manually by using the ungroup function. Forgetting to do this ungroup step is a common gotcha and a common cause of confusion when working with multiple group summaries. Another common task that you might need to do is to reorder the levels of a factor. Within R, factors are stored as integer values, which are then mapped onto a set of labels. Only factor levels that appear within your data will be assigned as a coded integer value, and the mapping between factor levels and integers is going to depend on the order that the labels appear within your data. This can be really quite annoying, particularly when your factor levels relate to properties that aren't numerical, but do have an inherent ordering to them. So in this example, we've considered data on the t-shirt size of 12 people. These aren't numerical, but they have an order. Annoyingly, the sizes aren't in the order we'd expect, and we don't have anyone who wears an extra large t-shirt within the sample. And what this is going to lead to is some really quite awkward summary tables and resulting plots as well. We can fix this problem by creating a new variable where the factors are explicitly coded in the correct order. We also need to specify here that we shouldn't drop the empty groups as part of that group by command. And we do this by setting .drop to be false. So I'm going to wrap up this lecture by highlighting some special data types that you should take really sort of a special care when handling. These are quite specialist topics, but ones that you'll encounter relatively frequently as a data scientist. And so I'll link out to some really helpful resources and packages to get you started on working with these more complex data types. As we've seen a little bit already, categorical variables can cause issues when wrangling and presenting data in R. All the problems that you'll face are absolutely solvable using base R techniques, but the forcats package provides tools for the most common of these problems. Some example functions from the package include functions to reorder a factor, either by the value or the frequency of another variable. And there are also functions for manually changing the order of a factor, or for lumping together levels of factors that are seen only very rarely into a single other category. Examples of each of these functions can be found in the forcats vignette or the factors chapter of R for Data Science, both linked here. The second topic to be wary of are strings. Working with and analysing text data is really a skill unto itself. However, it's useful to be able to do some basic manipulation of character strings programmatically right from the get-go. Because R was developed as a statistical programming language, it's really quite well suited to the computational and modelling aspects of working with text data. But the base R string manipulation functions can be a bit unwieldy at times. The string R package, in the same way as the forcats package, aims to combat this by providing useful helper functions for a range of text management problems. Even when you're not analysing text data, these can be useful. So, for example, to remove prefixes on lots of column names. These string R functions do assume some knowledge of regular expressions. So, unless you plan to work extensively with text data, I'd recommend that you look up these string manipulation tools as and when you need them. The strings section of R for Data Science is a really useful starting point here. So, do you remember all that fuss that we made about storing dates in the ISO standard format? That was because dates and times are complicated enough to work with before adding in any extra unnecessary ambiguity. We should always be storing dates as year, month, day. Data that concern dates, times, or time intervals have to reconcile two factors. The first is the physical orbit of the Earth around the Sun, and the second are the social and geopolitical mechanisms that determine how we measure and record the passing of time. This makes the history of date and time records really quite fascinating, but it can also make working with this type of data very complicated. Thinking first from the largest and then to the smallest time spans, we have lots of complications. Leap years alter the number of days in a year. Months are of variable lengths, and February's length changes from year to year. If your data are measured in a particular place that uses daylight savings time, then one day a year will be 23 hours long, and another will be 25 hours long. And to make things worse, the dates and the hour at which the clocks change aren't uniform across countries. These changes might be in distinct time zones, and the boundaries of those time zones themselves have changed over time. Even at the level of minutes and seconds, we aren't safe. Since the Earth's orbit is gradually slowing down, a leap second gets added approximately every 21 months. And nor are things any better when we look at really long timescales or across cultures, because then we might have to account for different calendars. Months are added and removed or altered over time, and different calendar systems used in different parts of the world take different approaches to measuring time and use different units or origin points for their calendar. With all these issues, you have to be really careful when you're working with date and time data. Functions to help you with this can be found in the Lubridate package, with examples in the Dates and Times chapter of R for Data Science. The final category to be alert when handling is called relational data. When you have data that's stored across two or more data frames, you need to be able to cross-reference those and match up values for a single observational unit. This sort of data is known as relational data, and it's used extensively in data science. The variables that you use to match these observational units across data frames are known as keys. The primary key belongs to the first table you're considering, and the foreign key belongs to the secondary table. There's various ways to join these data frames, depending on exactly what it is that you want to retain. First up, you might want to keep only observational units that have key variables in both of the data frames. This is known as an inner join and shown diagrammatically on the left-hand side here. You might instead want to keep all units from the first table, but pad with NAs when there's not a corresponding foreign key in the secondary table. This results in what's known as an outer left join. Conversely, you might want to keep all units from the second table, but pad with NAs where there's not a corresponding key in the primary table. This is imaginatively named an outer right join. The final common join that you might want to consider is the outer full join. In this case, all observational units from either table are retained, and all missing values are padded with NAs. Again, we've got diagrams showing each of these on the right-hand side of the slide. One thing to be aware of here is that things do rapidly become complicated when keys don't uniquely identify observational units in either one or both of the tables. I'd recommend you start exploring these ideas with the relational data chapter of R for Data Science. Okay, so why exactly is relational data so ubiquitous in data science? This is because businesses and companies don't store all of their data in a single huge CSV file. For one, this isn't very efficient because most of the cells in that CSV would be empty, and so it would take up an incredible amount of memory storing all of those empty cell values. Secondly, it's not a very secure approach because it doesn't allow you to grant partial access to the data. That's why information is usually stored in many data frames, more generically known as tables, within one or more databases. These databases or data silos are created, maintained, accessed, and destroyed using relational database management systems. These management systems use code to manage and access the stored data, just like we've seen in the dplyr commands. You may well have heard of the SQL or SQL programming language and its many variants, which are a popular family of languages to use for database management. In fact, SQL is the inspiration for the dplyr package and the verbs that it uses. On top of this, there's another package called dbplyr that allows you to easily translate your dplyr code into SQL queries, so you can write code that looks and feels like R code, but functions on databases rather than tuples. If you'd like to learn more about this topic, then there are many excellent introductory SQL books and courses, and I'd recommend you pick one that focuses on data analysis or data science, unless you really want to dig into things like efficient storage and querying of databases. Okay, so let's wrap the video up here then. We've met a lot of new functionality from the dplyr package that can help us to wrangle tabular data. I also introduced the idea of relational databases, and we saw that languages for database management, such as SQL, were the inspiration for these dplyr verbs. Finally, I raised some red flags on other data types that can be particularly tricky to wrangle. Things like factors, strings, dates, and times. These are types of data that everybody finds difficult to work with, so dedicated tools have been developed to make the process slightly more manageable for you. You've now got the tools and resources to wrangle the most common types of data that you'll come across as a data scientist. Thank you very much for your attention, and I'll see you in the next video.